All right. Hello, everyone. Today, we're going to be talking and continuing on our discussion of nonlinear models. So if you'll recall from last time, we went through this procedure to look at approaches to essentially fit data that has a nonlinear structure. And so we went from this sort of examination of doing polynomial or stepwise regressions, and then proceeding to sort of more complex regressions, looking at the formation of splines, right? And so we looked at things like cubic splines, natural splines, and what was the last one? Cubic splines, natural splines, and smoothing splines. And so these are sort of more evolved versions combining strengths of both the polynomial and stepwise regression, but then making the lines continuous at the points where you have breakpoints, and they turn into knots instead, right? And we even looked at maybe a hybridized methodology known as generalized additive models. And these are a way to essentially independently apply splines to variables so that you can understand visually, at least, the effect of an individual variable on the outcome. So with splines, one of the things to keep in mind is that you are still kind of using a transformation of the original functional form, right? And you're adding these constraints, for example, on smoothing. But there is actually a totally different approach that can be taken as well, that is actually also commonly used, which we'll talk about now. And so that is a kernel regression. So we're actually going to see in our example how this can replicate some of the estimation power that we're seeing in the splines, but it's going to be doing so in a very, very different way. So let me actually, we'll start a new screen here. So kernel regression. And what I'll do now is I'm going to write out the formula. So y hat is equal to, and this is going to look quite a bit different. And again, this isn't something that you'll need to memorize, but we're going to walk through sort of exactly what's going on here. So in here, we're going to look at this value, h. So h is known as the bandwidth. And the larger it is, the more we consider farther points. And the smaller it is, the more we consider local points. Okay, so here is the concept. If I were to have a couple of points, something like this, and we wanted to estimate without creating a fit, right? So without making our line here, if we wanted to estimate points of X and predict what they would be, you can imagine that you can use sort of local data to do so. So in the traditional way, we might have a line here. And if I wanted to say, okay, what is the X at, or what is Y when X is at this exact point? Well, I can draw a line and figure out it's right here. Okay. But instead of doing that, suppose I still wanted to know X here. So at this X, what is Y? And so we can actually do something kind of similar to K and N. And so I might intuitively say, well, I'm closest to the points in between these guys, maybe over here. Right. And so if you have a kernel based on weights, we weigh things more heavily if they are close. So the effect of these 2 points is going to have a larger determination on where this single point ends up compared to these points over here, which are, let's say, sort of farther away and exert less influence on that point. And so that goes back to this idea of the bandwidth, right? And so if you were to consider just the local points with a small bandwidth, you can imagine that this point here wants to be close to these guys. If your bandwidth is really large, so let's say the bandwidth looks something like this, but if the bandwidth is really large, then actually what ends up happening is whatever criteria that you're using to determine the placement of the point, all of the other points are going to be equally weighting. And so in this case, suppose that we wanted the average distance between the points that we care about. And so in the overall one, if the average line looks something like this, then our point would go up. And so depending on your bandwidth or how close you want to consider that point, the larger the effect of local or farther points are going to have. So hopefully that all makes sense. And I mentioned that in some cases we would consider something like the average distance, right? And so this is the k of x term. And there are a couple different categories that you can use here, and I'll talk about 3 of the most common ones. Okay, so first of all, we have a box kernel. So this is where k of x is equal to 1/2 if the absolute value of x is less than or equal to 1, or 0 otherwise. So if you remember the equation really quickly, y is equal to sum I k of xi minus x over h times yi over sum I xi minus x over h. So you can see in this term here, so this term can either only take a value of 0.5 or 0 um, in the box kernel. And notice that it is dependent on my bandwidth here. And so the larger the bandwidth is, you are dividing by a larger number, which makes your kernel smaller. And so this term here is essentially strictly limiting the ability of points outside of the bandwidth from making contributions in the valuation here. We've got a Gaussian kernel, and that looks something like k of x is equal to 1 over root 2 pi exp negative x squared over 2. So this is a normal distribution. And the way that you can think of this is that points that are closer to the x of interest will have a high value, and then they will fall away in the shape of sort of a normal distribution as you get farther and farther away from your bandwidth. And the last one, I'm not going to try and pronounce this, but this kernel is something like this. 3/4 1 minus x squared if x, absolute value of x is less than 1, or 0 otherwise. Okay, and so this kernel method is kind of similar to the box kernel, but these three together constitute common common kernel methods that can easily be applied essentially to create nonlinear fits that aren't necessarily based off of any functional equation, but rather are determined by the data itself and where it lies relative to any point of interest in your explanatory variable. So this is kind of the math behind, or the basic math behind some of the kernels, but we can see how they're actually implemented. And hopefully this will give you a sense of how powerful some of these kernels can be. So I'm going to jump on over to RStudio. Okay. And here we're going to use this exact same function from the last class to generate that non-linear um, non-linear set of points. So we're creating our x and our error term, and then our y. Okay. And we should have a plot here. And just as a reminder, what the linear model looked like. And adding that into the plot. Okay. So let's run all of this. Plot our x and y. And so if you remember from last time, we've got a set of points that looks something like this. We have a sinusoidal wave pattern that changes in amplitude and has an overall slope. And if you remember, when we apply a simple linear model to this, actually, let's make this red. We can see an averaged sort of line that captures the slope of this overall piece, right? But we know that unfortunately, while it can capture the linear portion of your model, the true model is not being well represented. And that's the piece that is sort of describing this sinusoidal wave pattern. Okay, so we need to use a library called NP. And so this is, as you can see here, non-parametric kernel smoothing methods. So go ahead and load that up. The first thing we're going to do is order our x's. So think about why we would need to do this, right? In order for you to pass information on the bandwidth accurately, when you fit the kernel model, you want to reorder the estimations so that you can actually draw the line correctly. So this is kind of an index that we're going to hold on to for later. The kernel model itself knows the order, so you don't need to do anything there. And fairly straightforward, we're using a function called npreg, and you're doing essentially like a linear regression form regressing y on x to do the kernel regression. And we're going to have a setting here known as your bandwidth. And remember, with the bandwidth, right, your bandwidth normalizes the difference between the predictions when it's big and magnifies it when it's small. And so let's go ahead and run this and see what happens. So you can imagine that unlike a sort of linear regression, there aren't any sort of coefficients, right? This is kind of just drawing a line based off of data on its neighbors. So there's nothing really to say about a specific pattern that you can infer from the fit. So it does give things like your error and your r squared, but it's not able to necessarily um, tell you anything about like a coefficient value that would describe this. And so let's go ahead and plot the fits. We're going to add in the original as before so we can have a comparison. So let's see if I run these guys. The red line is our true function. This is essentially what we know to be the real line based off of our function. And let's add in the predicted one from our kernel regression. So here I have to order the points as I was mentioning before. We use fitted instead of predict for the kernel model. That's the function that's coupled with the kernel model. Okay, and you can see here the blue line. Okay, pretty close, right? And so we have one of the things to notice is that with the amplitudes and sort of that middle area, that a lot of the splines actually did have some trouble with before, are actually doing pretty well with the kernel. Okay. And so here we can see that with this particular choice of bandwidth, the predicted values are actually fairly close to the true values, right? And so what I want to do now is to explore the model changing our bandwidth values. So again, as a refresher, right, the bandwidth, the larger it is, the more you consider points that are far away, and the smaller it is, the more you consider local points. And if you remember from the kernel regression, um, I have something like, oh, hang on. If I have the equation, it looks the kernel regression, the kernel piece looks something like this, right? And so H normalizes xi minus x when big, and H magnifies xi minus x when small. Okay. So this term, are you dividing by something large, which makes it small, or are you magnifying it x minus x by decreasing the size of your bandwidth? So we'll see what happens. So I purposely kind of started in the sweet spot, and let's go smaller and think about what's going to happen, right? So the bandwidth magnifies the differences when small. So let's run this. And zoom in. So hopefully you can see this. We're definitely getting some additional squiggliness, right? Um, and so it's really starting to favor the importance of localized points. And so you're getting some jitter that we might consider to be like overfitting. And in fact, we can amplify that even further by increasing, or sorry, by decreasing the bandwidth even further. So we started at 0.05 bandwidth, we went down to 0.01, leading to this, and now we're going to decrease it by an order of magnitude 0.001. And let's see what happens. And you can see at a certain point, once your bandwidth is small enough, it's essentially going to try and jump to almost like every individual point, right? And so this is the example in class where, I basically tried to connect every point, and we say, okay, well, there's clearly some overfitting happening. And so that's why you want to have a sort of balance between your choice of bandwidth and being able to try and approximate the normal the actual function versus getting to a point where you're doing overfitting. Okay. Oh, there's a blower outside. Hopefully that's not causing too much noise. So now let's go in the other direction. Oh, actually, let's rename these. Okay. Kernel model. I'm just going to copy and paste my code. Kernel models 2 and 3 with those bandwidths. And let's go the other direction. I'm just going to copy and paste here. So in this case, where I started at 0.05 and we were shrinking the bandwidth, now we're going to go the other direction. And here, starting with a bandwidth of 0.1, which means I'm doubling it, making it larger. And so you can think about what you would expect to happen once I'm starting to go in the other direction for the bandwidth. So I run this, and essentially it's starting to decrease the amplitude of the points. And the reason for that is essentially you're looking at the average value across a larger window. And so any variation will sort of naturally be dampened as you add more points into your window, at least in this example. So let's continue onwards, increasing the bandwidth by a factor of 10 each time. So this is a bandwidth of 1. Okay, and you can see here, it's not quite a straight line, but basically you've eliminated all of that sinusoidal waveform. But it does take into account like the window is big enough that maybe it's considering this half and this half, something like that. And so on average this is lower, on average this is higher, so you still do get some kind of curvature. And as I go all the way up to a bandwidth of 10, you can see that it just converges to the average value, right? And so this is what I had mentioned earlier when we were doing the whiteboard. Essentially, once you get to a certain point, the bandwidth basically says, okay, consider all of the points in your plot equally. And that's going to basically say the line should just be the average value of all of your points. Okay. And so as you adjust your bandwidth, you can see that the fit to your data is going to be vastly different. And so the question is, how do I go about deciding the proper bandwidth? And of course, the answer is cross-validation. So I can do that pretty easily here. I'm actually going to use my old formula to do the cross-validation. And if I run it across a sequence of different bandwidths, we can see what happens. So CV results. And so if I look at all of my mean squared errors across a range of my bandwidth values, the lowest one ends up being approximately 0.025. And this would be the one that's leading to the smallest out of sample errors. And indeed, if I run this, we can see in this particular case what the shape looks like. So this actually looks a little bit more jittery than in the 0.05 case that I had shown. However, this is actually the one that's doing the best in terms of out of sample predictions, and it's probably close enough, right? So there you have it. That is our example of the kernel regression that takes a very, very different approach to fitting to data compared to our splines, but you can see ends up with similar results. So you might ask a question, when should I be using a kernel regression versus a spline? Oh, and I should also mention before I get to that, hang on, let me jump back over. In our kernel regression, one of the things that you can do is set the you can set the kernel type. So that's CKER type. The default is the one that I said I wouldn't pronounce, the Apaneshnikov. I think that's how you say it, Apaneshnikov kernel. But there are settings for other types of kernels, like the box kernel or the Gaussian kernel that you can put in here. And those will help predict slightly differently. But I think in practice, generally, the bandwidth is going to be sort of more important to how you do your prediction. Okay. So going back to the whiteboard, mentioning the point I was bringing up, which is when to use splines and when to use kernels. So splines versus kernels. So splines, faster computational speed, slightly simpler to set up, especially with multivariate, and clarity of controlling curve directly, right? I can modify the curve based off of a specific function that is defined by the spline. Whereas with the kernel, it cares more about the data as they relate to your bandwidth. Kernels tend to be easier to program, easier to analyze mathematically, um, easier to extend to multiple variables, because bandwidth the bandwidth can encompass multiple variables, if you want it to, and combinations of discrete slash continuous variables is easier. Okay, so that covers two sort of classes of approaches as we think about non-parametric methods in application to regression. And because we've moved somewhat into this territory of these sort of non-parametric approaches, we're going to pivot a little bit again today to think about um, something slightly different um, than regression, but is sort of common in data analysis. And that is unsupervised learning. Okay, so everything we've talked about in class so far has been has fallen under the category of supervised learning. And what is the distinction? So unsupervised learning examines undetected patterns in data. It focuses on settings with only explanatory variables. No response variables. Okay, so this is your most important distinction. Everything that we've done has a y, right? So there's the y variable is some kind of function of all of our x's, whether that's in a linear regression, a logistic regression, and in all of these, splines and kernels, right? We always have some kind of outcome that we're sort of calibrating to. So think about what that means in the data. So you might have like y, x1, x2, x3. But you may have something where you have data that just looks like this, and you're not really interested, or you don't even know what the y should be, and you're not really interested in making any predictions. You want to understand whether or not there are sort of subgroups within the data that relate to each other, right? So imagine you have something, this is just for illustrative purposes. 1, 2, 3, 4, 5, 6. And then you have data that looks like 10,000, 10,000, 20,000, 50,000, or something, whatever, right? So there's something fundamentally different about some slices of this data. And you might say, okay, these kind of like belong in different groups, right? And so unsupervised learning is essentially a way to help get at problems like this, right? So this actually doesn't have anything to do necessarily with an outcome variable. It's more about identifying patterns in the data itself. So not interested in prediction. It wants to identify subgroups in variables or among variables. And importantly, this type of approach is unable to conduct validation. Okay. So what is validation in our sort of traditional sense? It is when we come up with a model that fits to the data, and then we compare what that model fit says about an outcome against the actual outcome. And in this case, there is no actual outcome, right? There is no y variable that we can compare to. And so all of the stuff that we talked about in terms of doing like cross validation or like k-fold, that all gets thrown out the window here. You don't have the ability to say that some grouping is right or wrong. There are two primary approaches. One is actually one that we've already talked about, and this is known as principal components analysis. This is typically for data visualization or pre-processing. So when we had used principal components, it had been for principal components regression, where if you recall, we take a set of data and we look at the variance across each of your independent variables and combine them. Uh, and from there, right, that's the whole thing where we went from y on our x's, and we transform the x's to some form of z's. So many x's to fewer z's, and then you regress instead on this. And so this was one of the dimension reduction activities that you can use, right? And so this procedure is known as principal components regression, but this part right here, where you do the reduction, is the principal components analysis that you could do as unsupervised learning. The other one, which we're mainly going to focus on today, is clustering. And there are a couple different methods that you can use here. So the first is k-means clustering. So this is a simple approach to partition data set into k distinct non-overlapping clusters. And k must be pre-specified. Okay, so how does this work? So the math here, just kind of for reference, looks something like this. This is the number of observations in kth cluster times the sum I prime element of ck sum j equals 1 to p of xij minus xi prime j squared. This is one of the mathematical formulations that I think is a little bit more complicated than the actual procedure of k-means clustering shows. And so, again, you're not going to have to memorize this or anything, but let's walk through the algorithm for how this works. So randomly assign 1 minus k to each observation. Iterate until no more changes. So basically, you're giving each observation an index value. And then for each k cluster, we're going to compute the centroid. And then assign each observation to cluster with closest centroid. And this can be based off of Euclidean distance. So no, anytime we're doing any distance-based measurement with data, you have to do some scaling. Normalization can be important. So this is typically actually a pretty fast procedure. So to give you some sense of how this looks, let's say we have some data that looks like this. Let's do this. And then we have data that looks like this. Okay, so let's suppose that all I'm doing is measuring the centroid of my red points. So that might look something like this. Okay. And then I measure the centroid of my blue points, and maybe that looks something like this. What the k-means clustering does, right? If you follow the algorithm from before, so we just did step 2A for each k cluster, compute the centroid. So we figured that out. And now all I'm going to do is every observation in the data set, I'm going to reassign its cluster based off of the closest centroid. So over here, let's say this point is closest to red, this is closest to red, this is closest to red, and this is closest to red, so that's going to get reassigned. And then over here, this is closest to the blue, this one's closest to blue. So these guys, and I think this guy up top is closest to blue. So now I will iterate, right? I reassign and then do it again. So let's draw our points with their new cluster. Looks something like this. And it looks something like this. Okay. Now I'm going to recompute my centroid, which I think is going to be something like this. And for the blue, it might look something like this. Okay. And then I reassign all the points. And what you'll see is that all of these guys are going to stay into the respective clusters. And so in this case, I'm done, right? In my iteration, and if I look at my algorithm over here, I will iterate until no more changes. And so in step 2, after my first iteration, the reassignment of the variables resulted in no changes. And so we're done. Okay. And so this is, yeah, a fairly simple algorithm that allows you to do this clustering. The tricky part is in that plot over here. We said that there's only 2 clusters. So k equals 2. And in this particular example, maybe it's obvious, but unlike most of the other sort of approaches that we've looked at, where the sort of parameter selection that determines a lot of how things are fit can be validated in some way, like through cross-validation. In this case, you don't have that, as we had mentioned, right? And so the decision for how many clusters is actually fairly arbitrary. Okay, so let's take a look at an example of this implementation in R. So I'll jump back over to R. And let's load in a couple packages to do this. So we are going to use ISLR, data table, and ggplot. Okay. We're using a data set called Auto from ISLR. We change that into a data table. And let's look at the data first just to see. This contains a small-ish data set, about 390 entries, that contains information about different types of cars, their fuel efficiency, number of engine cylinders, size of the engine, horsepower, weight, acceleration, so on and so forth. And so what we're going to do is we're going to look at specifically two categories of fuel efficiency and horsepower. So that looks something like this. And we are going to essentially see if we can cluster this data in any way. Oh, first of all, before I proceed with the k-means algorithm, remember we need to scale the data. Because the units, right, on horsepower versus mpg are very different. And so if you do Euclidean distances, it's going to much favor clustering based off of mpg rather than horsepower. Or sorry, it's going, no, that's right. Because horsepower is like much farther spread out. So we're going to do a series of k-means using different values of k. It's actually, fairly straightforward to do this. You just feed in the data that you want to look at. So we're doing auto scaled, which just contains our two columns, and then we're having two clusters. And I'm going to repeat this a couple times to look at different numbers of clusters. Okay. And we need to, essentially what I'm going to do here is I'm going to create some new columns based off of those outputs. And actually, we can take a quick look at what this returns. Okay. This first value tells you the centroid values of your clusters. So we have two clusters. The first one is at 0.466 mpg and negative 0.54 horsepower, but remember that this is the scaled version, okay? And then likewise the centroid for the other one. And then within the data, it is telling you essentially which cluster any individual data point belongs to. So in row 1, there's a vehicle, and we think that that goes to cluster 2. Same with row 2, 3, 4, and so on, and up to here. This is row 33. This belongs in cluster 1. Okay. Cluster sum of squares by cluster. This is actually a measurement of essentially that has to do with the distance within each cluster to of all the points to the centroid. And this is actually a rough procedure, which I'll talk about, that people do use to maybe help determine the proper number of clusters, although it's still somewhat arbitrary. This isn't like a direct validation or anything, but I would treat it as kind of a rule of thumb, which I will talk about in just a little bit. Okay, so what we're doing here is taking the results of our k-means and adding the assignment vector, so this thing, into the original data so that I know which row belongs to which cluster. So here, the way you do that is $cluster, and that tells you the assignment. So if I were to just run this, I can do that, and it gives me this vector. Okay, and I am also going to do that for each of my clusters. Great. And what I can do now is plot it. So it's going to be the same plot as before, only this time we are going to add a color. So that's going to end up looking something like this. Okay. So you can see there are two clusters. And so you have some kind of centroid here and some centroid within the red points. And that's how it will sort of arbitrarily, but um, in a specific procedure, divide the data into two clusters. And we can look at this exact same plot um, as I add more and more clusters and see how it decides to split the data. And in fact, it's not always necessary for the clusters to be sort of totally even in size, although with this particular example, it might be. And lastly, with 5, let's see, okay, something like this. And here you can start to see that the clustering, the size, the number of observations within a particular cluster doesn't need to be the same, right? There are fewer points in cluster 4, which is the blue cluster, in the upper left compared to, let's say, some of these middle clusters. Okay. So this is a fairly simple procedure to do clustering. And hopefully you guys get a good grasp of what's going on here based off the algorithm and the example that I showed earlier. The procedure to do this is actually fairly straightforward, and k-means is a fairly common procedure to do unsupervised learning. All right. Jumping back to the whiteboard, what we'll do is to talk about one last example of clustering. And this is known as hierarchical clustering. Oop, let me use a different color. Okay, hierarchical clustering, also known as bottom up or agglomerative clustering. This is an alternative method that does not require reselecting. Okay. Oh, that actually reminds me. Sorry. I didn't talk about that last thing about potentially how you choose K in the K means. Let me if I jump back over, I'm gonna lose this whiteboard, but that's all right. Okay, let's do that first before we talk about hierarchical clustering. Sorry for going a little bit out of order here. Okay, one sec. Okay. So there's a couple of different ways that so while I mentioned they're all going to be sort of fairly arbitrary, but there are a couple um procedures that people have taken to um try and use some quantitative method to determine the number of clusters that you should have. One way is to see okay, so one way is called the elbow method. Um, let's see here. If I look at the data or outcomes from my model run. So within cluster, sum of squares by cluster, you can look at this ratio here between sum of squares and total sum of squares, 59.6. So I believe this is K means $2 within SS or total. Yeah, here we go. So use your total within cluster sum of squares. So the elbow method basically looks at a plot of your k-means total within sum of squared values across various numbers of clusters. So that would look something like this. Okay, elbow. So we looked at 2, 3, 4, 5. So there's um, 4 values. Actually, we can do something like this. K equals 2 to 5. And then within SS is equal to, and then I have to grab all of these guys. Actually, we'll do it like this. Total within SS. 3, 4, 5. Okay. Okay, so what I'm doing is I'm setting up a data table that contains each of the total within sum of squares values, um, ideally we should have more. Yeah, let's do a couple more really quickly. Or let's do four more stairs. 6, 7, 8, 9. Same thing here. Easier to see the point of this in a second. And I will copy and paste this. 6, 7, 8. Okay, so now my elbow table has a couple more. Great. So if I go ahead and plot this, x equals k, y equals within SS. Whoa, hang on. Oops, that should go up to 9. Yeah. So our plot looks something like this. And usually the idea is that you choose your K based off of like I don't know. I've always felt that this is kind of a sort of silly way to do this, but imagine that like this is somebody's arm. You're supposed to choose the location of their elbow, um, which is like where the kink happens. So that might be like something like this or like this. It's determined by kind of where the slope of a line through all these points would kind of flatten out. So I would say probably like 5 or 6. Um, that's the elbow method. It's not the best approach, but again, like this is again something that there is no validation procedure, right? Since you're not dealing with any Ys, and so any sort of way of doing this is somewhat arbitrary. The decision here to do this elbow piece has to do with the fact that like you're getting essentially diminishing returns as far as your um we'll call it an error. It's not really an error, but like the distance to your centroid uh decreases as you add more and more clusters. And so we're trying to figure out the least number of clusters where you can kind of get somewhat close. And so once you start getting into the diminishing returns area, is where you say, okay, I don't need to add any more clusters. So for this plot, I would say the elbow is probably at 5 or 6. Um, and there are a handful of other methods. There's something called the silhouette method, um, which is also another sort of common way of doing this. But at the end of the day, it's gonna be somewhat arbitrary, and there's not much you can do about it. Okay, and so that is actually one of the nice things about hierarchical clustering is that you don't need to pre-specify. Okay. And this will end up with a tree-based representation. And this is known as a dendrogram. The way this works is it divides the data into kind of like a tree. Um, maybe it looks something like this. Okay. And the nice thing, as I was talking about in terms of specifying your clusters, it sets up the entire tree like this. And then if I wanted to do a certain number of groups, I can choose where to cut my branches. So that might look something like this. So that if I cut here, then you have two clusters. If I cut right here, I've got three clusters. And so, and then if I were to cut down here, I've got five clusters. So the nice thing about this hierarchical clustering is it preserves all the information about however many clusters that you want within your system, all the way from one cluster to n clusters, where n is the number of data points. And the farther up the tree branches fuse, the bigger the difference between leaf observations are. So the actual data points of your data set might look something like this. And these are the leaves. Okay, and so really important. Well, okay, before I get to that. So you can see that D and C are fairly close because they fuse. Let me use a different color actually. D and C are pretty close because they fuse not that far up, right? And then D and B will fuse farther up. So D and B are more different than D and C, and D and E, F, G, they don't fuse until here. Or it's, sorry, not there, here. And so D is much more different to E, F, G than they are, or relatively different compared to C and B. And a common mistake here, no conclusions can be made on horizontal difference. So yeah, this can be a common misconception. So horizontal doesn't mean anything. It's all about vertical. So in this particular example, like A um, in comparison to B, C, and D, I don't know if A is closer to C or D than it is to B. Just because it's closer horizontally to B does not mean that in the sort of procedure that we're using that it's actually closer. Okay. Okay, so let's talk about how this algorithm works. Okay, each observation is its own cluster. So you have a total of n clusters equal to the n number of data points. Then the two most similar are fused. So you have n minus 1 clusters. And I continue until only a single cluster is left. And this procedure will let me go from n clusters all the way down to one cluster, right? What does similar mean? So similarity based on Euclidean distances, right? And so this means that we have to do normalization if the scales of the data are different. So this is for individual points, but then think about what does that mean for similarity once we're talking about clusters. So this is based on something called linkage. And there are three different ways you can do this. There's complete, there is single, and there is average. So this is the largest dissimilarity. This is the smallest dissimilarity. And this is average dissimilarity. Average and complete tend to have most balanced clusters. And what I mean by balanced is that the size of the clusters are similar, or the number of data points contained within each cluster. So what this means is, suppose that I have data that looks like this. When I'm doing the similarities to do the fusion process, right, to decide whether the branches should fuse, the largest, so if I were to do complete, it would compare this point. Oh, let me use a different color. It would compare this point with this point. If I were to do single, would take the smallest dissimilarity, and that might be something like this point and this point. And then if I were to do the average, it would take something like the centroid and compare them. Okay. So these different linkages to do this similarity comparison, complete single average, can actually result in really, really, really different clusters. And we're going to see that in just a moment. So let's take a look at the example in R, jumping on over to R Studio. We can just do it on the same example. So HC complete, we're going to use an algorithm called hclust, which stands for hierarchical clustering. And you use a function called distance, and we put in all of our data. And we can specify the method that we would like to use. Oops. Average. Same thing, except at the end, I'm going to use the average method. And lastly, single, we're going to do this. Okay. Fairly straightforward, allows us to do this clustering. And let's take a look at the plot, which is going to be a little bit crazy, but that's all right. Okay, so we're going to plot the complete, the average, and the single. And let's take a look. Oop. Oh, what did I do? HC complete CX. Oh, put a period there instead of a comma. All right, now it should work. And let's zoom so that we can see, or see a little bit better. I know it's still going to be a little bit crazy. Okay. So this is the dendrogram of our hierarchical clustering using the complete method. So each leaf of this dendrogram represents a single vehicle in that auto data set, right? This is the 392 data points, and you can see the entire tree laid out. And in fact, you can't actually really see it visually here, but I could actually draw a series of lines horizontally through different branches to look at the clustering. And you can actually do it in such a way that you can go from 2 clusters to 3 clusters to 4 clusters systematically down, actually all the way to 392 clusters, right? If I look at the plot of the dendrogram, one of the things that you'll notice is if I look at the way that my branches split, at each one, they've got two branches. Okay. And you can look at basically any set here and you'll see that there is actually a relatively ish even number um, of branches when I look at each of my cluster groups. It's not entirely balanced, but it's fairly balanced, right? So if I were to do two clusters, about half of the data points are in the left cluster versus the right cluster. If you were to do four clusters, you can see that you're starting to lose some of that balancing, right? There's like a couple of cluster points here. And this is a lot less than, say, this branch. And so maybe the balance is a little bit skewed. Okay. But compare that against if I were to do, well, okay, let me look at the average one for, oops, I think I accidentally hit run all. Okay. So in the average uh, method of the hierarchical clustering, it's again somewhat similar, although, you can see that this left-hand cluster has quite a bit fewer than here. Um, and so that's one of the artifacts of the procedure that you decide to use in your clustering algorithm for hierarchical clustering. Generally, people will tend to favor like the complete approach because you tend to have the most balanced clusters. Here's the average one, and let's compare that against the single, which tends to have the least balanced clusters. Yeah, so you can see here, like if I do two clusters, you'll see 331 is on its own cluster compared to like everything else. So if you had two clusters, it would just have this guy out by itself. Okay, and so you can see the shape of this dendrogram really shows you kind of the um, unbalanced nature of this approach. Yeah, and so this clustering method, the way that it ends up leading to these like very small size clusters, this could be used as a different type of tool, right? You could use this as like an outlier identification, like which points are the most different from everybody else, right? And so the decision to use a particular method, complete, average, versus single, depends mainly on the context of the problem that you're trying to approach by using hierarchical clustering. Similar to k-means squared, I can go back and assign the clusters back into the original data to see kind of what that looks like. And the way that I do that is something like this. From I'm creating a new column in my original data set called HC clusters 2 because I'm going to have an assignment of each data point to one of two clusters. And the way that you determine that assignment is using a function called cut tree, essentially. You're right. That makes sense. You're like cutting the branches of the tree. And so this is going to give me that assignment. If I run this and we look at the auto data set, I can run back here and see. Okay, come on. Here we go. These are the k-means clusters that I had from before. And then here is the hierarchical HC dot clusters that I've just assigned. And I'm going to go ahead and do this a couple of times. And you can do as many as you want here, right? Because the HC clusters store all of the data um, according to your dendrogram tree. So if I wanted, I could do 100 clusters. That might look a little bit crazy, but let's see what happens. So I'll go ahead, run all of these guys, and then we can plot it. I will use our plot from before, but I'm going to replace this with HC and our number of clusters. And I'm actually going to add one more line here because I suspect we're going to get into trouble. With the legend, because there's going to be too many data points. And actually, well, okay, let's see what happens. So with the complete, that looks something like this. Actually, let's take a look at, let's do this. Let's also look at a version of the single with two. This. So we can see how different the clustering looks for single. Okay, right. And so it's clustered all of these data points, and then there's one data point that's kind of left out here. So again, this might be an interesting way to pull out outliers. Actually, I want to, now I'm interested, what point it's going to pick out for number 3. I don't know, maybe this point here, maybe this point up here. Let's take a look. It looks like, oh, I didn't change this number. Okay. Okay, so actually the cluster is a little bit bigger. We've got a handful of points right at the edge right here. Okay, great. And we can see how different that looks from doing the complete cluster, which divides everything into these 3 groups. And then with 4 into these groups. And notice, right, the cluster 4 here looks quite different from our k-means clustering, right? There's a lot more data points, a lot more balanced. And again, it depends on how the data is organized and whatnot. And let's see. Okay, I don't think this is going to work because I don't think ggplot has a default setting for that many colors. So maybe we might have to decrease this a little bit, but let's see what happens if we have 100 clusters. Okay. Oh, maybe it does. It's kind of hard to tell the difference between some of the colors, but because they're kind of dispersed, you can hopefully get a sense of what the clusters look like. Remember that there's 392 data points and we have 100 clusters. And so you're usually going to be anywhere between like 1 to like 8 points in a cluster. So that's a point on itself. That's a different one, even though the colors look very similar. Yeah, and so you can see kind of where all of your clusters are within the data as you basically cut the tree at different points along the dendrogram. Okay, and so that is the procedure to do clustering. And we've covered, right, two approaches today, our k-means and our hierarchical clustering. And just recall that this is a version of unsupervised learning, which is vastly different from all the regressions that we've been doing. So this is not a regression. This is a form of unsupervised learning that lets you find underlying patterns in the data as it relates to the data itself. These procedures do not have an ability to do any validation. There are no actual clusters that you can reference to validate. And if there were, we would no longer be considering this a unsupervised learning task. You would actually be trying to do some form of regression, right? And so this kind of procedure can help you identify specific characteristics of the data or split the data into chunks that you can then do different types of analysis with. But again, this is fundamentally a very different type of analysis than any of the regressions that we've been doing. So that's it for today. Hopefully this is all clear to you, but definitely feel free to reach out to me if you have any questions. And yeah, I will see everyone back in person on the week of the 22nd.